Hey guys, today we're going to cover lesson 4.6, looking at congruence in right triangles. And we're going to look at a shortcut that we have mentioned briefly in the first part of chapter 4, and that is called the hypotenuse leg theorem. All right, so just a quick refresher and reminder. The shortcuts that we were allowed to use so far would be side, 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 angle, side, angle, and angle, angle, side. So those are the four shortcuts that we have been using. Some shortcuts that we came across that we avoided would be SSA and angle, angle, angle. So AAA and SSA. Okay, these are ones that do not prove congruence. All right. Now, we always have exceptions in math, and we're going to talk a little bit more about this SSA combination along with the hypotenuse leg theorem. So, first off, we're dealing with a right triangle, and let's just focus on this triangle to the left here, ABC. This is a right triangle. We have a right angle there as angle B. And in a right triangle, we have what we call the hypotenuse. That is the longest side, or the side that is across from the 90-degree angle. And we also have the legs, which the legs, they are the two sides that touch the right angle. So we can call it leg 1 and leg 2, or just leg and leg there. And what the hypotenuse leg theorem states is that if the hypotenuse and leg of one right triangle is congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So we have hypotenuse and hypotenuse there. We also have leg and leg. And here we can use the hypotenuse leg shortcut. So originally this looks like side-side angle. We have a side, and an angle here. But because this is a right triangle, we can change side-side angle, which we cannot use, into HL. So that is the one exception with SSA. If you have a right angle, then we are allowed to use SSA, but we call it HL, hypotenuse leg. All right, that angle must be a right angle. All right, so let's look at a quick proof here. So in our first example, we have a lot of information that is given to us here. So I'm going to cheat, and for our statements, I'm just going to copy the given there. And the one thing that we do want to add into our picture is that last part of the given where it says AB is congruent to DE. Now we want to use the given. So there's actually two things that we can use. I see this term bisects, and I also see the symbols for perpendicular. So for our reasons, we're going to use definition of bisect. And as also, we're going to use definition of perpendicular. So with the definition of bisect, it tells us that BE, which is this line, is going to bisect AD, So AD is the line that's being bisected. It's being cut in half there. So we can add our tick marks to each side and write in our statement that AC is congruent to DC, AC, DC there. All right. Now we're going to talk about definition of perpendicular. The first definition of perpendicular that we're going to use is AB is perpendicular to BC. So we have these two lines that form a right angle. And we also have DE forming a right angle with EC. So we have, for our next statement, we're going to say angle B is equal to 90. Angle E is also equal to 90 through our definition of perpendicular. Okay. And as we move through our phases, we're in phase 2 of our proof. So we've used the given. Now we're going to use our picture. And we see we have this hourglass. And we have vertical angles. All right, so we have ACB. Angle ACB is congruent to angle DCE. And now we do have enough information to move into phase 3 where we find our shortcut. So what I want you to do is just look at your picture for a moment. We're going to focus on that. And let's just imagine that these right angles are not there. Let's pretend they're not there. Right now, for each triangle, we have angle, side, side, angle, side, side, which we mentioned in the first part of chapter 1, or chapter 4, that we cannot use SSA or ASS. We cannot use that rule. So the vertical angles here, they really do not help us. So we're going to backtrack. Let's imagine that the vertical angles are not there. Again, we have angle side side or side side angle. However, this time that angle is a right angle. And when that angle is a right angle, we are allowed to use SSA. However, we disguise that as hypotenuse leg. So we are able to use HL here. So for this proof, we really could eliminate the fourth step. We do not need the vertical angles. We did not use that in our HL. But you could leave that in your proof if you would like. It's just extra information we did not use. Okay. So just a quick proof on working with HL and the difference between side-side angle and having that right angle and how that allows us to use our new shortcut. Okay. In our last example here, we have two triangles, and we have our right angle along with the hypotenuse and the leg. So we are using HL here to say that they are congruent. And now we have to find the values of X and Y. So first I'm going to start out by looking at the legs. We know that they are congruent to one another. So I'm going to take X minus Y y minus x, and set that equal to x plus 5. And then we're also going to take the hypotenuse of each triangle and set those equal to each other. That would be 3y plus x is equal to y plus 5. So we have two equations that are created with two different variables. So what we have here is a system of equations, and we're going to use those methods from Math 1 to solve our system. There are actually three methods that you can use. There's graphing, elimination, and substitution. Any of these three methods would work. I'm going to choose elimination as our method of choice here to solve for this system. So the first thing we need to do is we need to get all the variables on one side of the equation and the constants, the numbers, on the other side. So we're going to subtract x here in my blue equation to get the variables together. And we're also going to subtract y in our green equation here. And we end up with y minus 2x equals 5. And 2y plus x equals 5. Okay, so we have our system with our variables on the same side. Now the goal is to eliminate one of the variables. We could eliminate the y's or the x's here. And to do that, I'm going to take that first equation and multiply everything by -2. We're going to distribute that -2 to all three parts. So that would result, we have -2y plus 4x equals -10. And for the second equation, we're just going to rewrite that equation. We're not going to multiply anything out there. And now we are able to combine these two equations. We're going to add these two. And we will see that the y's will end up canceling out, hence the name elimination. We're eliminating those y's. 4x plus x, that will give us 5x, equals a -10 plus 5 will result in -5. So quick one-step equation here. Divide both sides by 5, and we get -1 for our x. So we've solved the first part here. We found one of the variables. Now we're going to take that -1 and substitute that back into the original, into one of the original equations. So I'm going to take -1 and plug it back into, we'll do the first. So we have y minus -1 is equal to -1 plus 5. And we end up with y plus 1 is equal to, this would be 4. And we subtract the 1 from both sides. And y is equal to 3. So together, our answer would be x is equal to -1, y is equal to 3. Again, we used an elimination to solve this system. You could use the other two methods as well to arrive to the same answers. That'd be graphing or substitution, if you prefer those over elimination. All right. This wraps up lesson 4.6. Complete the homework check and the practice. If you guys have questions, please get in touch with me. Have a good day.